In the previous section, we have learned how to use steady space tools to model the linear circuits. So in this section, we are going to learn how to use steady space average method to describe a continuous conduction mode pulse width modulated power converter. So let's first consider a pulse width modulated converter in CCM. PWM converter in CCM. So CCM means continuous conduction mode. It means that we have two operation modes in one specific switching period. For mode 1, it occurs from 0 to dTs, where d is duty cycle, Ts is the switching period. So we can use a matrix equation to describe the state function for mode 1. Based on the equivalent circuits for mode 1, we can introduce a matrix function. So here is K derivative x over dt, where x is the state vector. As we mentioned, usually it includes inductor current and capacitor voltage, equals to a x plus b u. So where u is the input vector, and a and b are the coefficients correspondingly. So for the output, y equals to C1 x plus E U. So that is the output vector function. And we use C1e to represent the coefficients for state vector and input vector. So since those are the operation mode 1, so we specify them as A1, B1, C1, and E1. For the operation mode 2, we can do the similar thing. Mode 2 occurs from dTs to Ts. In the mode 2, we can also plot its equivalent circuit, which is a linear circuit. We can use the technique we learned in the last section to also establish such a matrix equation function. So we'll have k dx dt equals to A2 to indicate its mode 2 state vector plus B2 input vector, and output vector equals to C2 x plus E2 U. So the reason why we skip D is because we use D to represent the duty cycle of the pulse width modulated converters. Okay, so next step, we can do the average over those two modes. So we can build the average state equations. So mode 1 counts D proportion, mode 2 counts D prime proportion. So we can combine them together to do the average across two modes. So we'll have the first equation, average K matrix dx over dt, which is the identical to here, but the difference is that we do the average to the state vector over one switching period. And on the right-hand side, we combine those two together by doing the average. So this will be D proportion times A1 plus D prime proportion times A2 times the state vector x. And this part, we use the similar way. So will be D part B 1 plus D prime B2 times the input vector. Similarly, we do the average of the output vector in the similar way. So the left-hand side will be the average of the output vector over one switching period. Right-hand side will be D part for C1 plus D prime part for C2 state vector x plus D part B1 plus D prime part B2 input vector. Those are also for state vector and the input vector, those are also the average over one switching period. So after doing the average, we can, similar as what we did before, we insert the perturbation. So step 4 is we perturb. So there are multiple variables like average input state vector and average input vector, average output vector, and also we have the duty cycle D, right? And also duty cycle complementary D prime. So for those 5 parameters, we can perturb them. So one by one. First one is the input vector average, state vector average x. This will be equals to the DC bias plus small signal. So that is the state vector. Next, we do the similar thing to the input vector. So average U TS equals to DC quantity plus small signal perturbations. And similarly for output vector average. Also, it's DC quantity plus small signal quantity. And for duty cycle, so this will also be equals to the DC quantity, capital D plus small signal d. And also D prime. D prime is a complementary of D, so it equals to capital D prime minus small signal d. So till now, we have fully perturbed all those quantities in the averaged state equations. So next step is we insert those perturbed signal into the equation star. So step 5, we insert those perturbed signal into equation star. So we'll have two equations. First one is this one, right? The derivative of state vectors. So K derivative of this quantity will be equals to this one, which is DC plus small signal AC over dt. And for the right-hand side, we just perturb them one by one. So equals to the d equals to d plus small signal d cap times A1 plus d prime, which is dc d prime minus d cap times A2. And this one equals to the sum of DC quantity plus small signal. And next, for the second part of the right-hand side, which is similar, have the similar format, d plus d cap B1 plus d cap minus d prime minus d cap times B2 times the U average, which is this one. And similar, we can do the same thing to this output vector equation. Left-hand side will be the perturbed output vector, which is y plus y cap. And the right-hand side is those perturbed modified equations. So DC duty cycle plus small signal duty cycle times C1 plus d prime minus d cap C2 times DCX plus small signal X. Okay, and this plus the U part, D plus D cap times E1 plus D prime minus D cap E2 times the input vector. So that is the perturbed average state equations. So the next step, step 6, is we do the similar thing. We can linearize it. Linearize it. So we know that at steady state, those equations contains the DC quantities. So the DC terms on both sides, they cancel with each other. And also the second order AC terms, they can be ignored because they are much smaller than the first order AC terms. So by applying those two principles, we can significantly simplify those two equations, only keeping the first order AC term, right? For example, for the top one, we will obtain that K derivative x cap dt equals to ax. So this A is the coefficients for the small signal state vector, right? So if we compare those two equations, we can see that the combined A equals to d ay plus d prime a2. So it's like the average of those two coefficients matrix. And next will be the U part, right? So we introduce this B. So where B has a similar format equals to the average of B1 and B2. And we still have the D cap parts left. So we put them together. So we'll have the D cap term, which is A1 minus A2 x, the dcx plus B1 minus B2, the dcu times the, let me use the red chalk to indicate, times D cap. So this is the linearized average state equation for the state vectors, right? And next we do the similar trick to the output vector. So we'll have the left-hand side only keep the small signal AC term. Right-hand side, we have the X term. We introduce a coefficient matrix, which is C. So where C is the average of C1 and C2 plus the input vector parts, which is E. So where E equals to the average of E1 and E2. And also we have the D cap parts, which is similar to this one. We'll have C1 minus C2 dcx plus E1 minus E2 U times D cap. So this one is the linearized output vector equation, right? Vector equation. So based on the linearized fourth order AC equation, we can establish the equivalent circuits. But meanwhile, I'd like also to mention the DC terms. So if we look at the DC terms, we can have another results, which is the DC model, right? So basically, if we look at the DC terms, so we'll have the DC model. So for example, based on the top one, we can derive that 0 equals to a x plus b u. And based on the bottom one, we only keep the DC quantities. So left-hand side is y equals to cx plus eu. So this pair of equations can provide us the DC circuit model for the pulse width modulated CCM converters. Okay, so in this section, we have introduced how to use the state space averaging method to model the CCM mode pulse width modulated converters. So basically, essentially, this method has no difference with the previous learned methods, but we only introduced the matrix tool to make the entire derivation process more concise.